we're just saying about what were some candidate algorithms. So Shor's algorithm, Grover's algorithm, but there's questions here, right? How robust are these to noise? They, I think is widely believed, both definitely need error correction. Will we have error correction? When? How good will it be? Will we have thousands of qubits that might be needed in some of these cases? There's other candidates too, things like applications to quantum chemistry, but can it scale? Can we put in good enough initial states for the quantum computer to go the rest of the way? There's a really interesting paper by Garnet Chan and others from earlier this year questioning some of that. How precise can the answers become? Are they really competitive? What about physics simulation? Simulating, just having the quantum computers sort of pretend to be some kind of physics model. I would say this is going really well. This program is going really well. We'll hear on Friday from Michael Fossfeig about some latest results in literally doing that in real hardware now. So it's just a question then of like, how far can this be pushed? Can they resolve small numbers and low energy scales and these kind of things and really be competitive? And then machine learning. There were sort of multiple waves of machine learning with quantum computers going through, some of which got a bit of a black eye, but then there's some newer ones, and we'll hear from Ian Convey about some work connected to that, some newer paradigms for doing machine learning on quantum computers. So then there's just questions about, can we really see that there's a regime where the quantum computer will let us push? Arguably there is. Let us push beyond what we can do classically. But then there's a lot to figure out there. Like, can we process big data through what's the right way to use those tools? So I'd say that these are amazing devices and they're getting built now. So we should research what they're best for. And that requires, I think, a bit of like a conversation between not just classical computing as you might just find in a textbook, but really like cutting edge classical computing that's happening now that's responsive to what's going on in quantum computing. Some of the things that people know that classical computers can do aren't just available in a package. They're more available in the minds of different people, different experts, even work some of you could do just based on some of the tools I'll show you today. And so there needs to be this like ongoing active conversation, I think, between these fields, classical and quantum computing, that's actively clarifying the line between what's easy and hard. And among the different classical tools we have to simulate or to define this line, tensor networks are really emerging as the most powerful one. And interestingly, in kind of a twist, I don't think many people expected, including me, sometimes the tensor networks are becoming so powerful in certain cases that we can actually kind of flip the charge of the proof around or flip the script. And then these quantum algorithms that people had dreamed up, these kind of brilliant people like Peter Shor and people working with him, say, to define the quantum Fourier transform, for example, they had this great idea and they said, what is it for? It's to run on quantum hardware. But maybe that idea is just as good of an idea for classical hardware. Maybe the idea is great, but the only thing they missed was it's actually a good classical computing algorithm instead, just couched in this language of unitary circuits. So maybe these are even really good classical algorithms in disguise that we should just be already running classically. So where's that line? It's kind of the big question. So I'll try to hit on these topics. So let's step all the way back and just say why tensors, where do tensors come into this story? So really broadly, tensors might be something that some of you may hear that word and have some fear, because you'll sort of remember chapters at the end of a physics book about the Wigner-Eckert theorem, or you might have talked to a tensor expert and said, is it a multidimensional array? And they say, no, that's wrong. It's not. Somehow when it has two dimensions, it is, but as soon as it has a third one, all of a sudden you have to learn all this group theory or something, and that's just hype. It's all true. It's all true that there's a very beautiful literature about how tensors transform, but that's also true of vectors and matrices, and yet we use those every day without having to already know all that. So that's all there, but you only have to use it if it's useful for you. If it's not, you can just think of them as generalizations of vectors and matrices, and that's also a very good way to use them. So you can just think of them as multidimensional arrays, which is perfectly true if you know what basis you're in. And you always do in a quantum computer, because there's always a given basis of the qubits, at least, that you have. So so it's just kind of a multidimensional array for many practical purposes and for the purposes of what I'll be talking about. So things like a vector is just an linear array of numbers, and we could talk about its components. We could say, here's a vector V, components V1 and V2. Here's a matrix with components, M11, M12. An order 3 tensor you could think of as like a cube of numbers if you want, or some rectangular prism of numbers. So here by order, I mean, how many indices does it have? And I'll kind of use rank to mean more something like about factorizing them and that idea. But you see this notation is becoming kind of cumbersome. So we'll revisit notation in a minute. Where do we run into tensors? I would argue that if you kind of take a high enough dimensional view of any problem, that tensors are kind of lurking everywhere. So if you look at images, you could think that they're 2D, but really there's sort of a third index there, which might be the intensity of a pixel or a color value of a pixel or something like that. So it's really kind of an order 3 tensor in disguise. Or you could look at medical data and you'd have all these things you could say about a patient, and there's no sense in which, age and height should be the row and weight and symptom should be the column, and it's a matrix. It really kind of wants to be a higher dimensional thing. It also occurs really naturally when it doesn't even have to be something high dimensional. It could be something low dimensional, like a 1D, 2D, 3D function. But if you resolve it on a really fine grid, you could have a tensor that way. So this is the idea of discretization of functions. And last, but this is actually a really active area, I'll say right now, in tensor analysis. And then last but not least, and very much what we'll use tensors for in the rest of the slides here, is many-body quantum wave functions. So here you just naturally have a tensor because you have a bunch of small vector spaces here labeled S1, S2, S3. Let's think of these as the qubits that we're putting next to each other. And then the amplitudes just will have those labels, right? So the wave function, all the information is, the basis is just given to us. All the information's in the amplitudes. The basis has these labels S1 through Sn, and so the amplitudes will too. So it sort of wants to be a high order tensor, whether you want it to be or not. And that's what you have in your hands, and that's what you're kind of forced to work with if you try to work with the wave function itself. So we have this problem because it's a really big tensor, and we'll see that this is a curse, but then there's a way out of it. So in mathematics, this is literally what mathematicians call this problem. They call it the curse of dimensionality. It's that matrices, order 3 tensors, you can store them in a computer fully. But once you have an order, 8 or 10 or so tensor, you can't even store it in the computer, much less work with it in any practical way fully, like meaning it as a dense thing. And we can just do some simple counting to see why. So let's say we had a tensor that had 6 indices and each index ran over 10 values. It doesn't seem like big numbers, but then you just do counting and you realize that's 10 to the 6 numbers. So you can see it's going to go quite bad now if we are using this way to model a quantum computer and it has 50 qubits. We're going to have 2 to the 50 numbers. It's going to be really bad. So that's called the curse of dimensionality. So we have an exponential growth problem here. So there's different ways that I'll mention later to get around this curse, but the one we'll focus on is kind of a low rank idea, and that's the idea of tensor networks. So instead of storing all these numbers and treating them as somehow all individual units of information, we'll guess that they're related, and we'll store these smaller tensors that have, say, at most 4 or 5 indices, and usually more like 3 indices each. And then just you can sort of see how the counting goes, that each of these tensors won't require much of a memory footprint to store, and also it won't require a lot of heavy computation to work with. So we'll still be representing this big thing, but kind of in a latent, hidden way, like through these internal latent parameters that live in these other tensors, and that's how we're going to get around it. There's also kind of a more mild curse to dimensionality that happens with notation. So there's kind of a notational curse too, where you'll see in papers, people just write tensors as things with a ton of indices, but then the indices have subscripts, and sometimes the subscripts have subscripts, and it gets really bad. Or you might actually try to draw a cube or a collection of cubes, which is, it's really good, I think, way to teach what it is, but then it's not something you'd want to use as your main work tool, drawing 3D pictures, that wouldn't go too great. So we need a way to actually notate expressions like this and not lose track of what's going on or spend all our time writing these things down. And these are real things. This is a matrix product state in traditional notation. So this is the tool we'll be using for most of the talk. And I don't personally want to write it that way. Some of you might, but I don't. So we want to have a better notation for this. And fortunately, Roger Penrose, kind of out of his amazing mind, gave us a really nice tool to think about tensors. It's like fully mathematically rigorous, but it's also very inspiring for helping you to kind of see what's going on and to be creative about devising new algorithms and these kind of things. And then this notation, this Penrose diagram notation, that if you encounter a tensor within indices, you just make a shape, and the shape is a bit up to you. It's not such a standard thing. You could do, this is a rounded rectangle, you could do triangles, it's a bit of a local convention what shape you choose, but you just choose a shape and you have n lines coming out of it. And then we can see some examples that are more familiar. So a vector would be a thing with 1 line, matrix with 2 lines. Third order tensor would have 3 lines. And you can put the indices if you want, but you can also leave them off whenever it's obvious what they are, or the name is not important because maybe it's just being summed over as like a dummy index. Also, the direction of the indices can matter if it's helpful, but if it's not helpful, they generally don't have to matter. They can point any way that you want, just whatever makes sense for your domain that you're using this notation in. And the main other rule, other than what the symbols mean, is what it means when you join the lines together. So when you join the lines, that implies a summation. So it's inspired by Einstein's summation, but kind of goes even further, where you don't even need to put letters for the names. So you'll see in this first example, I still put the letters to help us keep track of what equals the traditional notation. But in the second one, I just left the names off entirely, but it still conveys exactly the same information. So you can think of this example here, which is a matrix times a vector. And in the traditional notation, you would have names for the indices. Then you would see that 2 of them match and that it's the one that's summed over. And you might put a line just to help yourself to keep track of which ones match. But then the idea of this notation is that line becomes this index line here, and you kind of promote that line. You get rid of the sigma, you get rid of the names. And what's nice is you can visualize what's going on. So you can see that whatever this thing is, it must result in a vector because there's 1 line left over. And then whatever this thing is, it must result in a scalar because there's no lines left over. All the lines are paired up. And you can see symmetries of the calculation. Like if I had moved this blue one all the way around, I get the same number. So you can kind of see the trace, cyclic property of the trace already there, just in the notation. And then, as I mentioned, if you have complicated expressions like this, if you write them in this notation, you can just see what's going on immediately. You can see what's connected to what. You can even do things like, I think I had an animation, where you can get rid of those internal indices. Here they have to have names, but here they don't, because the only thing they're there for is just to be summed over, right? So it's just this equally rigorous notation that I'll use quite a lot. So any questions about that notation for now, in case it's new to you, please ask. So let's pause here and do like a quick quiz. So just think for a minute about what would you say in traditional notation words is the first calculation example here, this first one, and someone could just speak up here in the room. Yeah, inner product of 2 vectors, right? Exactly. So that's a vector inner product. So if we put the labels and the names back, we can see it's exactly like what we would write. How about the second one? Trace, I heard trace. Yeah, trace of a matrix. Okay, great. Yeah, it is a kind of norm. That's right. And then I believe it's a kind of norm. And then what about the third one? This one doesn't have such a standard name, but just to kind of in words, how would you describe what it's showing? Yeah, like a tensor multiplication. Yeah, what are the kind of tensors involved in this one? An order 1 and an order 3. Yeah, exactly. It's just some order 3 tensor contracted with some vector, which is a really important operation in some algorithms. It's like you have a larger tensor and you want to analyze it by sticking vectors onto different legs one at a time. This is used in a technique called CP decomposition, for example. So that's what these mean. And that's also kind of nice. We have this kind of unified notation for things of different orders and different dimensions. So I think I convinced you all that that's a nice notation to use. So now let's use this notation and kind of step back a bit and make our way toward tensor networks and see where does the idea of a tensor network really come from. So it's this problem I mentioned earlier, this cursive dimensionality, that we can't store and definitely not manipulate a tensor that has n indices once n is more than 10 or 20 or something like that, depending on the size. And there's ways out of this, and all these ways people try today, and they're all good ways. One of them is if the tensor is sparse. Like for example, there's a very active field of people using tensors in machine learning, where even if the real tensor is not sparse, you only have a sparse view of it because you've only streamed in or collected a certain amount of data. So you just have the size of data that you have. It goes into the tensor, but you only know those elements. So you have a kind of sparsity of it. There's other kinds of sparsity that's just true of the tensor, even if you had all the elements. Other ways around this are that you can do sampling. There's other ideas, but sketching, these kind of things. But the one we'll use very much is the idea of finding low rank structure, whether it's exact low rank structure or approximate low rank structure. So what do we mean by low rank? Well, this is an idea that comes from matrix analysis. And I'm not going to be, way too rigorous here, but just to say that there's this kind of universal power tool that you can use for any matrix called the SVD, singular value decomposition. And it just says that given any matrix whatsoever, no matter how singular, how rectangular, you can always factorize it into U, S, and V dagger, where U and V are like kind of one-sided unitary, like if they square to the identity, if you multiply them on the big side. And then S is a diagonal real matrix in the middle. And you can always take S and split it in part and put it into the U and V. And then you have a factorization of some kind of A and B. And the idea being that the new index that you expose inside could be smaller than the outside indices. It might be a lot smaller. It might even be 1. And you can do this as either an approximation or as an exact thing, depending on the case and the context. So the idea is it'll run over just R values, and we call that the rank, however many non-zero values goes in there. So let's be concrete about this. Let's do kind of like a review. So let's say we had this particular matrix M is some kind of rectangular 4x3 matrix. And you might already see that there's some structure to this matrix. So low rank implies structure, or it comes from structure. So we can see that certain numbers repeat. The first and second columns are clearly related to each other in some way. There's also a lot of structure in the third column. So we just call the SVD routine, and it gives us the following U, S, and V, and we can see some of the nice properties that these have, like S being real and diagonal. So matrices U and V have orthonormal columns. So again, if you square them on the big side, they square to the identity. And then S, the singular values or the diagonals of S, they're always real, non-negative, and you can put them in decreasing order if you want. That's generally what the packages would give you. And then the nicest thing about it is it gives you a controlled approximation tool that you can use. So right away, packages will give you a thin SVD. So if any of the singular values are 0, usually they'll just already be cut away. And then you'll see the non-zero ones, but some of them could be very small. So what you can do is you can start with the smallest one and throw it away. And then you can measure, you can put it all back together, multiply back U, the truncated S and V, and see what, and let's call that product M2. You can just measure how far is M2 away from the original M, and it'll actually be exactly as far away as the square of the singular value that you threw away. Then you throw away the next one, it's the same thing, where now you take the sum of squares of the singular values that you threw away, and that will tell you how far apart the reconstructed matrix will be from the original one. And you can see as you look at these approximate matrices, they do a pretty good job. Like you actually get the first 2 columns right here. Here you somehow hang on to the fact that the first 2 columns are kind of similar, although now they're being forced to be the same. So it's starting to kind of break down, and then you get these kind of levels of controlled approximation you're allowed to do. And the reason this saves on computational resources is once you've thrown away some number of singular values, you can trim away the corresponding columns and rows of U and V. So you can already see just from this slide that there's a lot less you have to store in memory. And then if you do a little more work, you can also see this also translates into much less computational time, because your sums just run over smaller ranges of things that you have to sum over. So that's the idea, that you can expose low rank structure with the SVD, and you can prove that it's optimal. It's a sort of optimal low rank structure finding algorithm. Okay, so now the idea of tensor networks really arises from the question of, can we use the SVD on a tensor? Yes, I know. Mm-hmm. Oh, good question. Yeah, it doesn't mean anything too strong here. So I think people just have their own kind of house conventions about what they mean by the shapes. But there are kind of common conventions you start seeing people copying from each other. And one might be squares and triangles, meaning some kind of unitary or isometric property. That's a common one. And then circles often just means generic tensor with no particular properties or something like that. In the math field, I've noticed for diagonal tensors, they'll put a slash line through the tensor, which is like a nice notation. And there's other notations you might see. People might even use colors. So there's a whole thing. Good question, yeah. So the question becomes, how can we take an SVD of a tensor? And so one answer to this that I don't have any slides about, but there's an idea of maybe the right way to go here is to take some kind of symmetric SVD of a tensor where all the indices are treated on equal footing. This is a very powerful idea, and it leads to what's called the CP, canonical polyadic decomposition, which has some nice properties like some kind of uniqueness theorems you can prove. The other direction is this direction in the math community called tensor train, and it's a little bit more of like an engineer's approach in some way. It's a bit more, it'll be what I'll show you, but it turns out to be less symmetric, but have some especially nice properties where the algorithms you can do are all sort of provably optimal algorithms. Like the ranks you get are always the smallest possible ranks, and you have an algorithm in your hands to always get those ranks. So in the end, it's a very practical tool that I'll show you. It's this idea called tensor train or matrix product state. So you start approaching a tensor, a thing with multiple indices, and you say, can we use the SVD on this tensor? And you immediately realize you have choices. So you can reshape this tensor as a matrix. You could always group one of the indices, say that one index on the left and the other three on the right, into temporary row and column spaces. You could say that's the row, the other three together are the column. Let me be real precise what I mean by that, because that could be a confusing detail. So what I really mean is temporarily I take the numbers in here, and if you know like NumPy or Python, you might call the reshape function, or in Julia there's a reshape function. And you really just say, I will make up a matrix that's 2 by 8, and the first entry will be this one where all the indices are set to 1. The second index, this M12 will be start ticking through the indices on the right in some kind of binary counting way. M13 is I put the 2 there, then I go 2, 2, 1, and so on and so on and so on. Then, I can also change the column index to be 2 and so on. So you just make up a matrix that way. And then we can take the SVD of that very rectangular matrix. So that's one way we can kind of bring that tool over to a matrix. The problem is that there's other partitions we could have chosen. We could have chosen the first 2 indices to be the columns and the last 2 to be the row in the column, or the first 3 to be the row, the last to be the column. And we could even do other partitionings, right, that aren't left, right. So we could just take all those SVDs and just look at them all separately and say, well, these are just different views of the data. But it turns out you can actually blend them all together. You can do them all in some kind of compatible way where they like participate with each other. Before we get into that, let me say that let's just treat these reshaping steps as implicit. Let's not have to always say first reshape, then SVD, then unreshape. We'll just talk about the SVD of a tensor, and that means all those steps kind of put into a black box, right? So we can just cut a tensor somewhere. There's a U, there's a V, there's a S. And the U and V were like these tensorizations of those matrices, if you want. And we can do this at different places. So then we can use this tool or this set of tools to make this, to arrive at this thing called a matrix product state or tensor train. And this is what's called, physicists just call it doing SVDs to get an MPS, and mathematicians call it the TT-SVD algorithm. So what we do is we now just apply that tool one by one going from left to right. So we take the first index and we make it the row and the rest of the column. We do this SVD, and then we look at what we have. We have a unitary we could call U1. We have S1, V1. Or not really a unitary, actually an isometry. So we have all those pieces. We can save U1 off to the side and then multiply S1 over into V1. And then that new gray tensor there is just the result of doing that product. And then we can kind of detach them apart, right? So when they're attached, that equals the original tensor. Now we'll just put U1 off to the side and take S1, V1 as some new tensor. And we can just pretend that was the original tensor and kind of go back to step 1. So we can say, here's another tensor with 4 indices, right? Just like the first one had 4 indices, except now the new index here is this red index that came from the inside of the SVD. But we don't have to know that. We can just say it's another 4 index tensor. So we again cut, except now we cut where we always put this kind of latent index and then one of the external indices or physical indices on the left side of the cut. And then we do the same thing. We do another SVD, except this time we call the factors U2, S2, V2. We multiply S2 over, we leave U2 behind and say, thank you to U2, and it's kind of left behind now. Lastly, we do the same kind of thing where we're going to cut here and then, make the row space to be this latent index and then the next physical index. And we do one more SVD. And then now we just look at what we have. And we have this sort of chain of U's that we left behind. And then we have an S and a V, and we can move the S over to the last tensor. And then that's how we arrive at this matrix product state form. In the last 2 lines, all we're doing is just changing the drawing a little bit. Nothing has really happened. It's just putting a more generic drawing where we're a little bit more agnostic about the properties of these tensors. But if we want, this is also a really nice drawing, this middle one, where we can use special shapes to indicate that these U's, because they came out of an SVD, have some kind of isometric or kind of one-sided unitary property. If we want, we can use that. That's called a canonical form. And we could also notice that this last tensor has some kind of special property that essentially it's the entire tensor, actually. If you only truncate away singular values that are 0, this whole tensor got kind of rolled up into this thing, which is kind of interesting. So it's actually like we've smushed that tensor off into that corner. So there's all these different ways to look at it that are very interesting, and I don't have time to unpack all of them, but is there any question about that process that I just showed? Yeah, Tyler. Mm-hmm.
So if you have a tensor and a second tensor, then I agree that you have an order.
Mm-hmm.
But of course, like I can take a picture, think of it as a tensor, and then look at it here,
Mm-hmm.
and I get a different answer.
Yeah.
So like, what is the actual universal property here? Like, you kind of alluded to it, that the last one is sort of absorbent.
So there is a non-universal side to this. So you're hitting on something quite important, that that if you don't have a clear notion given to you of an ordering of the indices, then you still have to choose that. You still have to choose a 1D ordering, and that's kind of that's the biggest weak spot of this format. So this format is like a dream when you have a 1D property built in. So if you're doing like 1D physics, 1D circuits or something for quantum computing, things like that. Another place where it shines a lot is if you're doing 1D functions, and these indices basically tell you how far to go in some continuous space or something like that. But if it's just heterogeneous meanings to the indices, you don't really have a clear guide at the beginning of like what order you should put them in. And then this might not even be the best tool. Although it's such a powerful tool, sometimes you can just brute force your way through that. You can either just try all the orderings, or you can just pick one and it still might do a good job. So it's not the sort of perfect tool. And that's why there's other tensor networks, like for 2D quantum physics, there are these PEPs that try to get out of that problem. So hopefully that answers your question. Yeah, partly. But it's also partly to say there isn't a total answer to that question. It's sort of part of the issues with the technology too. And then another question right now that I saw. Okay. Okay, great. I mean, I will say that this is just one of many places you could put this tensor. It could be on the end, but you can put it somewhere in the middle too. And you can put it on the left side. You can also make trees with exactly these same steps. You just, instead of doing a left to right pass, you can do kind of pairs and then pairs of pairs, and it's really almost the same steps, and you can make tree networks as well. So there's quite a lot you can do just from understanding these few slides.
So when you say we look for different orderings and we can get worse or better results, I mean, for example, the rank is small or large, or what do you mean the quality?
Yeah, thanks for clarifying that. Mainly that the rank would be small or large, meaning either if we try to keep everything, we'll just get the ranks, we'll get into where we divide 0 from non-zero singular values, or we'll start throwing away numbers and seeing how we did. And we might find that the approximation breaks down very rapidly in one ordering versus another ordering. And I'll add that in physics, in kind of lattice model, condensed matter physics, there's a very deep and precise understanding about a lot of this. And this has to do with ideas of entanglement, the area law versus what's called the volume law, which kind of gives you a guide or a roadmap of saying, if you have a quantum system with some Hamiltonian that looks like this in this dimension, these are the ways you want to patch up or divide the system that will give you good ranks versus these other ways that won't. And basically, it's just telling you, respect the locality that the Hamiltonian actually has. Don't just randomly permute the sites, that kind of thing. But that doesn't help you if the Hamiltonian is completely non-local as much. Although we have some experts here, Joey, who could tell you that some twists on that story. But there's still some areas where we don't know what's the best ordering or the best tensor network to bring, or even if tensor networks can do the job at all. So there's a lot of open questions too. So I'm just going to show you more of the success stories today. Kind of taking a perspective on what we have in our hands here. Although that algorithm I showed is very useful and powerful, you had to have the whole tensor before to do it. So you had to start with an exponential and then pay this exponential to get to this nice smaller thing. So that's not very practical in the scaling limit of going to many, many indices or big problems. So what you really do is you actually just start with this form as an ansatz most of the time. So you just say, we imagine this big tensor that we can't store, we can't compute. We just imagine or wish for it to be this form over here. I should have made an approximate equals because that's more how we think of it. So although we can think of starting with that full tensor and doing a big chain to SVD to get this network on the right, more often we just think of this as a special submanifold of the space of all tensors. Then we want to go to that manifold and work there, and maybe move to neighboring manifolds defined by other rank sizes and things like that. And we kind of want to go into that space and work in that space, do algorithms that will help uncover what the right numbers should be in here to optimize those numbers, that kind of thing. So let's also talk a little bit about, once you have one of these things in your hands, one of these matrix product states, what are the benefits you can have? The name matrix product state comes from the idea that there's like a fast algorithm to retrieve any element of the original tensor that you want. So if you say, go get me the 0, 1, 1, 0, 1 element of the original tensor, meaning set those indices to that value. Once you set those indices to those values, those indices are quenched now, they're fixed, so we can remove them from the picture. And then we can just, I think I messed up the colors slightly here. It should be like light, dark, dark, light, dark. Okay, but you put the colors to mean which ones were 0 and which ones were 1. Then we see that that's just a chain of vector matrix products, right? That's a vector times a matrix times another matrix and so on, and there's another vector on the end. And there's an efficient way to do that sum, which is you just do vector matrix from one side across. So there's the result of the first vector matrix, and then the next and the next and the next, and you get a scalar. So just by doing a very quick set of products of these kind of R by R matrices, where R might be 10 or 100, nothing too big, we can retrieve any element we want one by one. Now that's not probably the most efficient way to use this though, because if we wanted to say compute the average over all the elements in the tensor, this wouldn't be so good because we'd have to go pluck them out one at a time. There might be much better algorithms to do that. And we'll see something like that in a second. But this would be, if you did just want to retrieve an element, that's a good way to do it. To give you a bit more idea about how to think about this tool, there's a key thing you could think of as like a hyperparameter of this format called the bond dimension if you talk to a physicist, or you could call it the rank if you talk to a mathematician. Really, rank is a better name. And we often call this chi, sometimes capital D or other names. And the whole idea is if you can get away with chi being fixed or sort of modest for your problem, like maybe if it can be held constant across a whole class of problems as you scale up, or maybe it just grows logarithmically, not too bad. Basically, if we can think of just working at some fixed chi, we obtain a massive compression, and we can just do counting to see that. So if we had the original tensor, which we may have never really even seen or been able to store, if it has n indices, all of dimension d, we can see from that earlier argument that it's d to the n numbers. But if we just do the counting over here, we have n indices, and n tensors, sorry, and each one has chi times d entries, except for the ones on the edge. So roughly we have n times d times just chi squared numbers on the right. And that's way less. We can see that the n, which is a thing usually we want to scale up and make bigger and bigger, maybe even make it infinite, that comes in front. It's no longer a power. And then we just have this kind of modest d chi squared polynomial overhead to work and to store these things. So storing them usually costs chi squared. Various algorithms cost either chi squared or chi cubed usually. And we can do tons of operations with about that scaling. So we can do operations like summing to MPS or multiple MPS all in the compressed form. So you don't have to leave this compressed space. You just temporarily jump from one manifold of rank R and R to another one of rank 2R, and then you can compress back to rank R again with a controlled approximation. You can multiply things together. So there's a close analog of an MPS called an MPO, matrix product operator, or you could just think of it as an MPS with doubled indices on each tensor, 2 indices instead of 1. So that's kind of like the matrix for an MPS, and you can multiply these together. And again, there's a set of nice controlled algorithms to do this multiplication, bound your error, perfectly what they call in math, rounding the ranks back to whatever ranks you want, and sort of getting a controlled algorithm for that. You can also perfectly sample these. So if they represent a probability distribution, there's nice algorithms that will just go in and draw one of the tensor elements for you with exactly the probability of that element squared, or if it's a regular probability, just the size of that element. And then the next draw is totally independent of the previous draw. So it really is just going in and plucking elements out for you with no bias about the history of the chain of the samples that you drew. And many other things like this. So there was one other algorithm I thought I'd show you in a bit more detail because it's easy to explain, and it kind of shows the power of these ideas. And that's just the idea of the inner product of 2 MPS, which could also be the norm of a single MPS if you want. So if you want to know its norm, or if you have 2 different ones and you want to compare them and take their dot product with each other. So I hope you can see that the dot product would just be contract all the shared indices between them. So just think of them as big vectors and just contract all the indices that they share. And then we could run over all these sums in parallel, and that would be this exponentially big calculation. But there's a much, much better way to do it. And the trick is you just contract from the side. So what that means is you say, let me contract 2 of these tensors together. And then when I do that, you can see that there's 2 lines coming out of that circle. So I have this temporary thing here, which is this gray tensor with 2 indices. Then I just grab another one, like say that blue one on the bottom, and I contract there. So that's, again, a small tensor contraction I can do. And I get that gray tensor, this intermediate. Then I just keep bubbling. I take the next red tensor, I take the next blue tensor, I go across like that. And if you sit down and kind of do the counting of the cost of each step, you'll see that the cost is something like n times chi cubed. Memory usage is proportional to chi squared. And at the end, you get a scalar like you should. Everything goes great. And when you really do the counting, if each MPS was represented a tensor that had 40 indices and each index had size 2, then if you think of these as vectors, they would have 1 trillion entries each. But in practice, this algorithm takes like 10 milliseconds on a laptop. So you've done a dot product of 2 vectors of size 1 trillion in 10 milliseconds to sort of perfect accuracy, double precision accuracy. And that's even if this chi is as big as 100, which is enough to solve most ground states in one-dimensional problems very accurately, for example. So you can see it's like a very powerful technique. And if we can do that, it's got to be useful for some other stuff too. That's kind of the philosophy of it. Any questions about that part? Because this algorithm is really like some details. Mm-hmm.
This is just a generic dot product process. Right? Mm-hmm. The speed up actually just comes from the fact that these two are approximations of block.
Yes, that's right. That's a really good point. So it doesn't. Oh, sure. Yeah. So he was saying it's a generic. If I understood right, you're saying it's a generic statement about these being these matrix product states. And the speed up comes from that and not because of anything about the larger tensors per se. Is that kind of what you're asking?
Yeah, so like this looks like a normal way that you're basically just saying how you would do the sum for the.
That's right.
That should apply for general vectors of whatever size it is.
General vectors in this format.
In this format, right.
Yeah.
But I guess the fact that you get the trillion example is because these two actually represents much larger.
Oh, yes, exactly. Right. So that's where there's a little bit of a dishonesty in a way to this slide, depending on your point of view, because I didn't actually go get those trillion numbers at any point, right? I never materialized those trillion numbers. So then in that sense, it's dishonest what I said, because I didn't do a hard calculation in that sense. But I think in the end, it is honest in the sense that if someone told me, no, you're being dishonest, that's the reason, I'd say, no, it is honest because what I did is I used the fact that there's some latent sense in which those trillion numbers are have some relationship with each other. And so I didn't need to materialize them. Like, for example, a very simple example of that would be if someone just told me they're all the number 1. Like if someone said there's 1 trillion numbers, but they all equal 1, what's the sum of them? I could say, well, okay, I have to be honest and literally add them all up, or I could just say it's 1 trillion, And so it's sort of a more sophisticated version of that same insight. It's like saying there's a pattern. We don't have to do all the work. We can use the patterns. We can use the structure. So there's just one particular kind of structure that can be there that we can use. And indeed, that's an important point too in another way, which is saying that because of just how much speed we got here, it cannot be the case that this will always work. Because if it was, we could just encode all kinds of NP-complete problems somehow into these tensors probably, or there's often very easy ways to do that. And then this would seem like we're saying, NP equals P, it's all solved, And so what goes wrong? What would go wrong is that these ranks, these bonds would actually be exponential in those cases. So if you try to put in problems that are too hard into these original tensors and then say, we've got a way to solve them, you'll find that what gives is that the ranks blow up. So there's some space here of medium hard problems that these are capturing for us. That, yeah, I hope that helps to, great. Okay, and then I won't say much about this. We'll mostly be using the MPS, but just wanted to point out that there are other interesting families of tensor networks that where you can take the same idea of just some arbitrary tensor with n indices and then decompose it all these different ways and see which one might give you some advantage on a certain problem. So there's the MPS, which in the end, it's kind of a workhorse because it has the best algorithms and the best scaling that we know right now of these families. There's the closely related tree tensor network, also called hierarchical Tucker network, which is a very close cousin of the MPS. It's just the MPS is like a maximally unbalanced tree, and then this is like a more balanced tree version. But you can get it through the same steps, these SVDs applied in different cuts and that kind of thing. But then something that's very different, but which is very actively researched, is this idea of tensor networks with small loops. The main example being this thing called a PEPS. Better name might be like tensor grid or something. And the idea is that by having these loops, it can be vastly more powerful. And there are already really good algorithms for it, but the loops make things kind of tough too. Some of the kind of guarantees we can give in the case of MPS and trees about certain steps being optimal and these kind of things, they start to kind of go away, or you have to pay a lot more to keep those guarantees. So that's why it's a more active area of research, I would say. Okay, let's see, how am I doing on time? So 2:15, and then I think I'm doing all right. So let me go through maybe a bit quick through this, and we can talk about it more later, but I wanted to give like a detailed example of an MPS, and this example will be pretty familiar to some people here in the audience. So let's consider a bunch of bit strings. And by the way, this has a little bit of a quantum computing flavor, if you will. It also has a little bit of a flavor of this thing in physics called SPT, kind of this idea of like sort of hidden orders and things in wave functions. Consider a collection of bit strings of length n. So that's just how many bits there are, but which have like kind of a subtle or hidden property, which is an even parity property. So if we count however many bits are equal to 1, we'll always find it's an even number. So it might be none of them, it might be all of them if n is an even number, or just 2 and another 2 somewhere else. So there's a lot of these, right? It's actually half of all the bit strings. So half do and half don't. Can we construct an MPS that sums all those up, or sort of is exactly 1 on all those bit strings and is exactly 0 on all the others? And this is a kind of thing that kind of reminds you almost a little bit of quantum computing problems. Like you might use Grover's algorithm to do this, where you say there's some oracle that will go and tag all the bit strings that are even, and then I want to go back and uncover these, and that sounds like it would be this extremely hard problem because you're thinking, man, that's like an exponentially large set, this could be hard. But we'll see that this is kind of solvable by MPS with a rank of just 2, actually. So we want an MPS that has this property. If I put bit strings on that are even parity, I get 1. If I put odd parity, I get 0. Those are missing. They're not in the tensor. So the main ingredient I'll just do a kind of constructive proof or a construction of this MPS is I need this MPS tensor that's going to be this 3-index tensor that's going to run through the whole network. And I'll just propose that it has the following properties. So if I set the external leg to 0, I'll just get a matrix, which I always will for MPS tensors. And that's just going to be the identity matrix when that external leg is 0. When the external leg is 1, I'll get like a kind of like a poly X matrix or like a C0 matrix because it flips the bit. So there's going to be a bit of information running through, and it'll be flipped or not depending on what bits come from outside and stick onto the external leg. So these are almost like little sluice valves, and there's some water running through, and these are going to raise and lower gates that's going to affect this information that's kind of running through the MPS. That's like a cartoon of it. Then we're just going to start the process in some starting state, and we're going to catch it in some ending state. And we're going to enforce that as it goes from the starting to the ending state, something happens in the middle an even number of times. And that's that the bit will flip over and then flip back an even number of times, which could be 0 times, So we'll start off in this state E1, which is 1, 0, and we'll have to end in E1, otherwise we'll get the number 0. And then we're going to count however many bit flips happen, and that's going to be how we make the MPS. So let's just see how this machine works as we put it all together. So let's just take a length 2 MPS with these choices, and we'll see that we start in the state E1, we put a 0 bit, so we get an identity, so nothing happens. Put another 0 bit, get an identity, nothing happens. And then we get, E1 times E1, so number 1. So everything is easy in that case. And I hope you can see that would just chain perfectly to any number of bits, right? It's just identity, identity, identity. We could also set all the bits to 1. And if there's an even number of them, this will go great as well, because we'll start with the starting state, we'll flip it. So now we're in the E2 state, but we'll flip it again, and then everything is back to E1 and we'll get the number 1. And then we'll see that, if we put an odd number, then, we'll have an odd number of flips and we'll get 0, right? It's pretty, I think you've got the picture now. So starting E1, there's a 0, everything is okay, but there's a 1, things are flipped, and now we're out of tensors and we have a mismatch. So we have E2 times E1, 0. So we see this will work, and we can see constructively that the bond dimension or the rank is 2, because all these matrices are 2 by 2 by 2 tensors, like all these MPS tensors are 2 by 2 by 2. So the longer MPS just works exactly the same way. So we can really kind of see what a matrix product state really looks like in this example. We can think of it as just kind of like these piano keys that you can play, and then the sound that comes out of the key is a matrix. So all the keys are up, and it's like identity matrices, and I press on a key, and now it's a bit flip matrix there, or I press 2 keys, or I press a bunch of keys. And so even though it's just very simple information, like a piano key going up or down, there's exponentially many different ways. If I have enough hands, I could press the keys all these exponentially many different ways, and I can hear these different sounds coming out of the piano. So that's kind of like another way to view this machine. Okay, any questions about that example? Mm-hmm.
How well it can adapt to being mislabeled in a sense, you perturb a few of them. Can it find a way to still capture almost all the accuracy, or is it die pretty fast? Can't really handle it's a noise in data.
Oh, okay. Yeah, great. So you're saying like, what if we just plucked out like one of the bit strings? We just said all the even bit strings except for this one or these three.
Yeah, so
That's really interesting. So I won't have enough time to like unpack that whole question, but we have basically a paper about that. Me and John and Ty have a paper roughly about this sort of reverse process where we say, what if we feed in many examples, but we feed in more and more and more? Can we see at what point you need, like when do you have enough to finally learn this pattern? And this pattern is a particularly hard pattern because it's like a global pattern. You have to, in some sense, see all the bits to see whether the property is true. It's very different from, say, like learning handwriting. Because handwriting, I could just show you little parts of it, and you could, after a while, you'd say, I'm pretty sure that's the number 7, But here, no matter how many parts I show you, you have no idea until I show you every single bit. So it's a very tough learning problem in that sense. But nevertheless, I mean, we did show in that paper that we could like predict for different length bit strings kind of when you would have enough data using MPS ideas. So there's a whole story you can put together, and I don't have it all prepared, but it's a great question. Now, kind of relatedly, you can also do a removal story where you could start with them all and everything compresses to rank 2. Then you could just start pulling them out one by one by one. And I believe, or I have a pretty strong sense, because I've been playing with some of this kind of thing recently in a different context, that the ranks will grow really fast. It's like, if you do that in some unrelated way, the machine is just being forced to basically memorize which ones are missing. And so it's going to need to spend another rank to kind of hold on to all the ones that are missing. And it's going to break down pretty fast. And you'll have like an exponential barrier to climb over. So this can relate to things like if you try to do SAT solving with tensor networks, if you know about that. So it's like enforcing rules on bit strings locally. If you enforce all the rules simultaneously, the rank can stay small. But if you enforce them one by one, there's this like exponential barrier you have to climb before you come back down. It's almost like y p doesn't equal np or something. It's like pretty interesting. So yeah, it's a neat story. Okay, and that brings us to quantum computing, which is some way out of some of these problems possibly. So now we've got this tool of tensor networks, matrix product states, which are kind of the workhorse of tensor networks, I would say. I mean, one comment on that. When I say they're the workhorse, like even those 2D tensor networks, the PEPs, the square ones, a very common way that we actually work with those is that if you look at the edge of one of them, it's a lot like a matrix product state. And then we just can push the matrix product state through the PEP. So they really are kind of like the building block of many of the other tensor networks in many ways. So just that's why I keep saying it's like the workhorse. So let's see how they connect to quantum computers and how we could use them. So what is a quantum computer? Well, it's like a machine, it's a computer made out of bits, but instead of being classical bits, they're quantum bits, right? That's the idea. So they're two-level systems, but they have some sense in which you can observe them in different bases, you can entangle them, all these other ideas that we know, quantum mechanics. They're programmable, that's important too. It's not just that any large quantum thing is a quantum computer, otherwise like a rock would be a quantum computer, right? You just cool a rock down and you say, it's a quantum. That's actually quite important because people will say there's this idea that quantum computers can do things that classical computers can't. It's kind of true, but that's true of a rock also. Like a rock can be something that we can't simulate also. So the programmability is utterly important. The whole idea that we can input instructions and those can be carried out, in hypothetically this exponentially large space, that's really what makes it a computer, not only that it's big in quantum, right? That's a picture of one of the computers at Google's lab in Santa Barbara there. What do the programs look like for a quantum computer? Well, these are called quantum circuits, and they're just like classical circuits in the sense that you can have gates that are like and or and not and these kind of things. But there's other gates that only make sense in this quantum world, like the Hadamard gate and things like that. And these are all unitary gates, and I'll be real precise about this in a second. And we draw these circuits that look like this, where these are the gates, 1-qubit gates, 2-qubit gates. These represent the starting state of the qubits. And then a point I'm going to make is that this is also a tensor network, quite literally. So every quantum circuit is in a very precise one-to-one correspondence with a tensor network. It's the same diagram, same rules. So these shapes are tensors, the lines are indices, connecting two lines means a sum is running over it. So all of that is exactly the same. So I haven't done anything on these two slides. It was a quantum circuit, now it's a tensor network. So let's see how that's the case. So we can first of all understand this initial state, which is very conventionally, the initial state is usually just a product of all the qubits in all the state 0. So how do we represent a qubit in a state 0? It's just a it's just a two-dimensional space, so it's just a vector of size 2. And the state 0 is just the first vector. It's just 1, 0. So this is just an outer product. I should mention there's kind of a third rule of tensor networks, which is if you put two tensors next to each other, it means an implicit tensor product or outer product. That's kind of a given background rule of the notation as well. So all these are in an outer product with each other. When we see these tensors with two indices, single qubit gates, those are matrices according to these diagram rules. So for example, that could be a Hadamard gate. So this unitary U could be the gate H, and that's what the gate H looks like. Could be the gate NOT, that's a NOT gate. And then there's two qubit gates, and these are the ones that really bring a lot of the computational power. So these are the ones that generate entanglement and take you off into this exponentially hard space for a classical computer to work in. An important one would be the controlled NOT gate, where it says, if the first qubit is in the state 0, don't do anything to the second qubit, but if it's in the state 1, flip the second qubit. That's what that gate does. There's also a controlled Z gate. So there's these different gates. So I'm just trying to be real concrete about there's specific numbers you can put into these tensors. And then the state after executing this quantum circuit is just given by contracting all the tensors. But already there's a clue there about why there might be some classical attacks or sort of ways in, because I just said contracting all the tensors. I didn't say from left to right or in what order, right? So that already there's an interesting topic about, do I have to do a given order or can I search over all orders? And there's packages and techniques. I don't have slides on this, but there's packages like Cotingra out of Caltech that will actually find the best order for you. And we also have that now going into iTensor, where it'll actually do heuristics to find optimal orderings for you, and then it might find a better one than sort of the nominal one. But let's just do the left to right kind of marching through order, and I'll just show a few slides just to show you, we can look at the whole wave function for a short period of time, but then after that, it'll start taking off into the exponential Hilbert space, and we won't be able to really kind of see it anymore. So we can first just see it as this outer product of all zeros, which is just the vector 1, 0, 1, 0, 1, 0. Then we can apply some single qubit gates, like say we apply Hadamard gates. So we now put them all into a superposition of 0 and 1. And this is interesting because now formally taking their outer product is now an exponential superposition of all possible bit strings with all equal weights. So this is an idea that I like to call like quantum parallelism. Some people don't like the word parallelism in quantum computing, but I think it's a fair term here. It's like we now have the potential to plug in every possible input to a function that takes binary numbers in, bit strings. So this is an interesting point to distinguish too between entanglement and superposition. So this is a sort of massive superposition. This is kind of maximally in superposition, but it's totally unentangled. So those are like concepts that can be related, but they also can be rather different from each other, superposition and entanglement. And it's really, both are responsible for the success of quantum algorithms, but it's entanglement that really is the one that separates quantum hardware from classical hardware in principle. That's really the thing that makes these things hard to simulate from a tensor network point of view, at least. Now let's bring in a two-qubit gate, and this will start adding entanglement. We already have superposition. We add entanglement by acting with two-qubit gates or multi-qubit gates. So we could act with a control Z, and then now we see that the state of qubits 1 and 2 is now some more arbitrary tensor that has all possible elements that could be non-zero now are. And if you actually did more analysis, you would see that there's entanglement now between the first and second qubits. Still, the rest are unentangled, just kind of doing their own thing. We could act, with another gate on the qubits 3 and 4, and you start to see that this thing is kind of now gradually turning into a more arbitrary tensor. And so it's not hard to imagine if I start acting with a gate between 2 and 3, 4 and 5, this thing is going to rapidly start filling up this space of tensors where all the entries, all the 2 to the n entries could be possibly non-zero. And that's what will happen. So we can't really write the numbers anymore after a few layers. It's just going to be some arbitrary tensor with as many indices as qubits after a while in general. So just some complicated tensor. But it's interesting because it's not just any complicated tensor, it's also this circuit. So there is structure in a sense. So even though this state might be a fairly kind of random state, it does have information in it, at least the information of what the circuit was. That's kind of an important point to notice about it, right? So in a way, the circuit is a compressed representation of this high tensor already, right as soon as we write it down. So there's all kinds of like structure in there, even if the numbers look very random when you look at them. And again, that structure has hints about that there might be sort of attack vectors on some of these algorithms and whether they're really easy or hard. But if the circuit is structured enough, and I'll get into what some of those things might be briefly, the state afterward might be close to a matrix product state or not, but depends. Like if it's shallow, if these gates are very special, this thing might actually accidentally end up being an MPS. Because MPS can handle all those things. Entanglement, superposition, definitely. Entanglement, yes, to some degree. So all those things are not exclusive to quantum hardware. Like you can have all those things in classical hardware too, up to a certain point. And in particular, we can use an MPS to actually run a circuit. We can always at least try. It might fail, but the interesting thing is it'll tell us, right? So it'll basically do great at first, and then at some point it'll start sending back a report to us saying, I'm having a harder time going to the next step, and the computer will slow down. So you can actually kind of like feel quantum mechanics as you run these algorithms on your computer. I mean, literally your fan will start like making noise, So it's almost like your computer is like yelling at you saying like, BQP hard or something, So you can actually like, it's very like, you get a tangible sense of like something quantum is happening inside your computer. Quite literally, that's what's kind of fun about this stuff, right? So we can literally use an MPS to execute a circuit, and right now I'll show you a cartoon, and then we'll actually break down the steps into something that you could all code yourselves. And if you want, I can help some of you to even use our package iTensor. If I had more time, I'd put some code examples, but I'll show you the steps. So here's kind of a movie, if you will, of what it looks like. You just start stepping through the circuit, and entanglement starts being generated by the algorithm I'll show you in just a minute. And so I'm drawing the internal ranks here as thin lines to say that the ranks can be always kept pretty small at first. That's always true. Then they have to grow a little bit. Then it's a question later of, do they stay small or do they shoot off to the moon? And that just is very, very problem dependent and approximation dependent. So by the end, you actually have, if it all goes well, or if you just pay an exponential price, depending, you have the entire wave function defined by the circuit sitting in your computer, and you can probe it and analyze it and do all kinds of things to it. By the way, I should say a bit of terminology is that's called an open mode simulation. So in some sense, it's actually doing something much, much harder, much more than what a quantum device would do. A quantum device would implicitly do all that, then just hand you one bit string at the end, right? I mean, there's other things you can do too. You can add little bells and whistles at the end of the circuit that implicitly probe many bit strings, but still that probe is reported back to you as like a single sample. So here you have the entire wave function just sitting in your computer afterward, and you can do all kinds of classical computing tricks. Like you can post-select one of the qubits, which you can't do in a quantum computer. You can force a qubit to be 0 no matter what, and things like that. Or you can get the norm of the state, which here is always 1, but you can do tricks with the norm also with non-unitary gates and stuff. So there's all kinds of like ways you can cheat classically that add a lot of power. So how do we do this? How do we actually run this process? There's many ways, and some of them are more sophisticated and more powerful, but I'll show you the like simplest way that has the virtue of both being pretty dang powerful and really pretty easy to code with the right software libraries. And this is called the TEBD algorithm, also called time-dependent DMRG. It has different names. Time-evolving block decimation kind of goes back to a paper by Giffray-Vidal. And so the observation is that we can just do controlled application of 1 qubit and 2 qubit gates. 1 qubit gates will be perfect and exact to machine precision and very fast. 2 qubit gates start out or kind of temporarily exact, but then we have to, they take us out of the manifold of matrix product states that we want to stay in. So we have to kind of pull back on this process after a while, and that will incur a small error, but we get to choose the error. So we can either, it's interesting, you can either work at fixed effort or at fixed error. So I don't quite have a slide about this, but you can either say, I will always only pay up this much per step and just see how things go. And then I might get a good answer, I might not. Or you can actually let the accuracy always have to stay pegged to some goal. And then that's when your fan of your computer will tell you what's happening. So it'll either run and you'll say, done, or it'll just bog down and your fan will start running. And you will be getting the accuracy, but it's just the time will blow up. So you can make these trade-offs and you can ask the algorithm, you can tell the algorithm what's more important to you, speed or accuracy. So first of all, let's see how a single qubit gate goes, just as a warm-up for the 2 qubit. This one, you can always get both speed and accuracy. So this one goes great. So let's just say we have this single qubit gate and we want to apply it on the 4th qubit at this step in the algorithm. So all you do is you just temporarily push the other tensors of the MPS aside. You just take the one that the gate is acting on, you just do this tensor contraction, which is just this matrix times tensor contraction. You know, it's easy to code, and you could even just code this in NumPy or using iTensor. It's just one line of code. And you see afterward, just by looking at the number of lines coming out, that this thing is already back to being an MPS tensor, 3 indices. The ones coming out are actually still the same ones with the same size as before. So then all you do is you just drop it back into the MPS. And so now you could reconstruct the whole state, same bond dimension, same costs. Everything goes sort of perfect in this case. I mean, so that already, by the way, gives you some sense about why there's an interesting conversation about what's hard, what's easy, because some of the more naive things you might read will say, you know, quantum mechanics is hard because it's in a superposition, or we're manipulating a quantum wave function. But here's an example where we're manipulating an exponentially big quantum wave function without any error at all in a very short amount of time on a computer. So some things are not hard. This is one of them, right? But some things are harder. So acting with a 2-qubit gate is a little harder and more approximate. So let's say we want to do that operation. So we just bring the gate on, and let's say it acts on the 4th and 5th qubit, like as shown. We see that only is going to change at most these 2 tensors. So we just push the other ones away. And then we just do this contraction of these 3 tensors together, and just in any kind of order, you know, pick 2 of them, multiply them together, put the other one on. We get this tensor afterward that has 4 indices now. So it's really not anymore following the MPS format, because the MPS format, all the tensors have 3 indices going through the middle. So we want to recover the MPS form. And the nice thing is there's a controlled way to do this. And I'm leaving out a little bit of some important details, basically being that you have to have already prearranged for those other tensors to be U's and V's. If you remember that algorithm where we cut, you have to like have arranged that to be the case, but that's very easy to arrange. And if it's not, there's a fast algorithm that will make it so. So you have to have all the ones that we pushed away to be U's on the left, V's on the right. And that's because that way they're kind of like a faithful orthonormal basis transformation into the basis that you're working in here. Then once you've done that, this is now a controlled step. So you take this tensor, you reshape it as a matrix, you SVD through the middle, there's the U, S, and V. And then what you do is now you do a truncated SVD where you keep the largest chi singular values. Another way you can work is you can just start summing up the small singular values from the bottom, and then just have a threshold where you say, once that sum of squares of singular values goes over that threshold, then we define chi that way. So there's different modes you can work in. So you somehow determine how many you're going to keep chi. Then you usually what you do is you know where you're going next. You say the next gate is going to go onto the right of this bond. So you push the singular values to the right. And that already keeps you in that U and V form, because we see we're going to leave a U behind on the left. Or you say the next gate's going to be on the left. So you push singular values that way, which is what I'm showing in this example. So there's some kind of smart details you can put in. And then when you've done this, you've restored MPS form, but it's an adaptive algorithm because chi might grow. It might have started out as one value here, and then afterward it might grow. And that's good. So the computer is telling you, you now kind of owe a little bit more work, but what you get back is fidelity to the true state. So it's sort of making some contract where you can say, I will agree to some extra computer work, but I will keep a very high fidelity to this target quantum state. You know, again, you can make the contract the other way. You can say, nope, I'm only going to do this much work, and the fidelity is just going to drop and drop and drop. And that's, by the way, a lot more like the experiments, because they just have the control that they have, and the fidelity just goes down and down and down in these near-term experiments. So they're more operating in a mode that's a lot more like they have a fixed chi budget. That's just the sort of level of control that they have of the qubits. Here we have 2 different modes. And so when we have these 2 tools, we can simulate any circuit that looks like this, and actually quite a few more, with this so-called TEBD algorithm. So it'll just look like this. The slide has a bit of a mistake. I put random, but it could be structured, it could be random. So we just start off and we start applying these gates. And if we work at a fixed chi in this example, we'll see the fidelity drop. And it might drop really low, or we might be happy and it may just sort of plateau at something very good. And I was kind of vague about where it plateaus. It might plateau at 99. It might plateau at 0.02. So, you know, there's these different values we could hit depending on how we work. Let's think about what could be some of the cases where this could go really well. So where could this succeed?
Miles,
Sure. Yeah. Mm-hmm.
The question is, can tensor network methods efficiently capture long-range correlation, classical or quantum in the system? MPS doesn't look very entangled.
Yeah, that's a great question. So the term long range gets and correlations gets applied in a few different ways. And so one has to kind of break it down a little bit. But the most traditional idea about correlations would be that you would take two operators that would like probe locally in the system. And then you would say, what's the sort of connected correlation function of these two operators somewhere, sites I and j. Then you pull them apart. And you say, as I go along this 1D chain of the MPS, that I'll see if the correlation function decays rapidly or slowly. And then it might be that the true state you're trying to model, say, has slowly decaying, like power law decaying correlations or something like that. The MPS can actually model that very, very well. But eventually it fails to do it. So out to sites of hundreds or thousands, it'll fit a power law. But then it always, you can prove, it's very easy to prove that it'll eventually cross over to an exponential drop. And so some states have exponentially decaying correlations, and for them, MPS is like a perfect fit. Some states don't, and MPS can kind of somewhat brute force them, or actually quite well brute force them, but then eventually it'll sort of have a slight mismatch. So there's a whole detailed understanding of which correlation patterns MPS can capture in those kind of more regular cases. There's another thing where, when I heard the word long range, sometimes people talk about another thing called like long range entanglement. So this is a concept that like Xiaogong Wen and people in topology had kind of pioneered. MPS can also capture them perfectly, and so can PEPs and these other things. So long range entanglement is sort of long range, although I think I would prefer to call it more like global. It's more like some kind of global topological property that just is throughout the whole system. And usually that only amounts to, say, the bond dimension having to be like 2 or something like that. So, so that kind of long range is very, very easy to capture with tensor networks. And it's more like something like saying that it's not the statement that the bond dimension has to be particularly big. It just can't be 1. That's all. It just needs to not be 1. As long as it's 2 or 4, you can usually capture that kind very, very easily. So those are some comments. But then there's also a whole activity of more complicated unstructured problems with tensor networks. There's like work by people like Stefanos Kortis and Eduardo Murciolo and like solving SAT problems with them. And I think the understanding is a lot more complicated, and we don't have a full understanding. So this is a whole subject. That's a very good question. Yeah, thanks. So kind of on that note of, what are these good at? When do they succeed? When do they fail? So in the worst case, like if we don't make any approximation error at all, like I probably should have not put this approximate sign on this slide, the bond dimension will just double every layer. And we can kind of see this from the point of view that when the outer indices are chi and 2, then the row and the column are at max 2 chi in size. And if you just look through the theorems on the SVD, that's the maximum rank. So worst case, that's what we have. So we have only a bond dimension doubling, which is really not that bad because powers of 2 grow pretty slowly at first, right? 2, 4, 16. These are not big numbers. So we can push through that for a little while. And what's neat is that these tensor network algorithms scale linearly in the number of qubits at fixed chi. So we could actually do thousands or even like hundreds of thousands of qubits for order of 10 layers without a big problem. Like this would all be polynomial scaling. So quite literally, I could take my laptop right now and simulate 1,000 qubits and do 10 layers of gates. And this would only take so long. Like for a few layers, it would only take seconds. And then for a few more, it might take minutes or hours, but that's it. So already these have a very interesting angle where you can't imagine these experiments right now today doing thousands of qubits and even doing 1 layer. So there's some ways in here where tensor networks are in some ways vastly better than quantum computers already today, but only in certain limits, like this kind of shallow limit. Yeah,
That's exact.
That's that would basically be exact. That's right. You could do that to kind of floating point precision. That's right. Yeah. So I think that's already very interesting that there's some things we can do now that quantum computers may not ever do. So.
Nearest neighbor to the gates. If you have far range to the gates, that'd be a big problem.
Not a big problem. It's a good question. So it would be a little bit of a challenge, but there's a thing you can do where at worst 2-qubit gates have a rank of 4 if you just cut them, because it's like 2 times 2, 2 times 2. So you can just stretch them out and you can make little transfer matrices that just pass that information along. And what I'm really talking about is an MPO. So you can make a long MPO that has the 2-qubit gate sort of going through it. And then we have controlled algorithms to apply MPOs to MPS. So you could just use that.
And that causes all, it used to grow in the middle, each side all will grow by.
That's right. So then all the bonds in between where you applied it will grow, but only by 4 at most. So it can go quite well for a little while. And it's kind of, it feels right because we know entanglement gets generated between those two far away. And if we're using this chain tensor network, this 1D chain, it has to carry that entanglement, something has to carry that entanglement all the way. So the MPO is kind of telling you like, you can't get out of this for free. Something has to carry that. Yeah.
That's the clarifying question, I suppose. So then when you had that, if you had, you know, in your diagram and said you had some, you know, screwy connection that goes up, then you just insert a matrix product operator. So you just add another layer that does that for you through the distance unit change. A bit like, well, it is changing a basis.
That's right. Yeah, you do these kind of internal basis changes. You can imagine that there's now vertical lines going through this picture that I don't have in this case, but which kind of carry this entanglement through the operators. So
and you can just control the penalty, that's incurred by moving space.
That's right. So I realize I kind of didn't watch my time totally, so I'll have to be kind of careful how long I spend on some of these. So let me try to land on the really good points here and then go faster through some of the obvious ones. So here's a more obvious one. If the number of qubits is small, you can do basically any number of layers, but that's nothing surprising because we could do a full state simulator on 4 qubits of any depth. So it's just the MPS version of that. The interesting part putting this together is that I got this idea from Matt Fishman for this slide. I like this picture, is that there's this whole kind of region of kind of tensor network simulability that's always true regardless of the problem. And it's either low circuit depth and you can go to any number of qubits, or low qubit number and you can go to any circuit depth. And then there's this kind of whole range in between, kind of interpolating between those limits. And then this is the direction of like increasing entanglement. And after a while, if it's moderate circuit depth and number of qubits going to more, you finally kind of you could hit an entanglement barrier. But I put the word might, and I put the word can always. So this is only kind of worst case, best case stuff. If the circuit has a lot of structure, you might even be able to go to huge problems and deep depths, but that would be a very problem dependent statement. This plot is showing problem independent simulability of these tensor networks. So now kind of wrapping up the talk, now I'm just going to do a little bit of future casting of, you know, what are things that are happening quickly kind of right now that I think pose some kind of exciting directions, and this is kind of to wrap up on the top. That's worst case things. That's saying worst case, we can just do a few layers or we can do a few qubits. Although, you know, a few layers on, you know, 1,000 qubits if we want. But for structured problems, this can all go actually quite a lot better. And there's some surprises, at least surprising to me, things that happened. So one of these is I learned from Chris Chen, who's here as one of the speakers for Friday, that this seminal algorithm in quantum computing called the quantum Fourier Transform, which you can see is a bit complicated. It's got these kind of long range controlled phase gates and it's got all these layers and a lot of history, and it's a key part of Shor's algorithm. It's basically the second part of Shor's algorithm. The first part puts the answer in, and this is the part that gets the answer out. That whole circuit turns out to be a tensor network of rank or bond dimension 8. It's really infinite bond dimension. It's just that when you approximate it by cutting off small singular values, you get about 8 when you say throw away ones that are below kind of machine precision. So that was amazing. The trick is that you have to reverse the order of the output classically from what is the standard order, but that's never a problem whether on a quantum computer or a classical computer. So this is to say that beyond just these worst case statements, tensor networks give us a way to very concretely sort of operationalize special cases of circuits that are both very useful, but also turn out to be very, very classically simulable. But let me note on this slide, Chris will have more to say about this. I'm not saying Shor's algorithm can be simulated because the state going into this part has to also be simulable first before you can do this part. So we're just saying if, you know, you can input easy states into this and do them, but if a hard state is still a hard state. So this doesn't immediately, you know, solve factoring. So nobody call the NSA or anything like that. So then, yeah.
Kind of clarify
Mm-hmm.
on the previous slide that's a circuit. It's sort of deep in the red zone, but it's because it's so structured.
Mm-hmm.
You know, it's like because it's so structured,
Mm-hmm.
it doesn't have the entanglement that one would expect.
That's right. That's right. It's like, exactly, it's deep in the red zone, as John said, because that statement about it being 8 holds for any number of qubits. So it's deep in the number of qubits in principle. It's a pretty deep circuit as well, kind of depending on how you organized. Some of those layers that are usually drawn separately can be combined, but it's still, it's a moderately deep circuit in some sense. It does something very powerful and useful, definitely. But in some sense, it's kind of only making small, kind of very special phase twists on the state that kind of decay very quickly as you go away from one qubit to another. So it's doing something that has a lot of structure, as you said. So that's like the key to why it's low rank. Then kind of, ending on some of these other ideas about how much these technologies can be pushed. One way they can be pushed is by starting to be more careful about, rather than just saying worst case, best case, we can be more precise about this exact algorithm in these typical cases and things. Another way we can push is just more through kind of raw power and just sort of clever algorithms like contracting things from the side, contracting things from different angles, using all the tricks in the tensor network toolbox. So even for rather unstructured problems, tensor networks can be competitive. So Google very cleverly proposed like kind of almost like a maximally unstructured problem as a challenge to classical computing. I won't have a lot of time to do this whole story justice, but in 2019 they pulled off, I think, still a very convincing experimental result where they programmed a circuit in, kind of roughly looks like this. You have all these randomly chosen single qubit gates followed by specially chosen but well-chosen 2-qubit gates. And you apply them and you try to keep as much fidelity as you can, but it's not an error-corrected computer, so the fidelity does run down exponentially. But they are managed to keep just this little tail at the end, this 0.02% accuracy back to the original state. And that was quite an achievement, actually, because it's a very, very hard circuit to run and it's deep, 20 layers and things. But when we tried it on we tried using this just simple TEBD algorithm that I already taught you all today, we tried like a 1D analog of the circuit. Theirs was 2D. If they had done 1D, we could just do it like that. We could have gotten the equivalent of a 99% 2-qubit gate fidelity computer in our laptop. So Google already knew that. So they made the circuit 2D. If Google had messed up and made the gates control Z rather than this other kind, we could have easily beaten them just by taking chi to be 300 or so. So they also knew that. So that's why I say it was such a good, well-designed experiment. They got out of every trap we could have laid for them. I mean, not because of us. I mean, they already knew about these traps. But just to show you how kind of neck and neck tensor networks and these things are. So finally, they did all the things right. 2D circuit, this hardest kind of 2-qubit gate. And there we fell way short. We only got 95% fidelity at every step, but still 95. I mean, it wasn't too bad on the other hand. It makes me start to think like, if you had put a tensor network in a box and you can only input unitaries and output bit strings out of this box, what are the cases where you could even tell whether there was a quantum computer in the box versus a laptop, right? And in 1D, we would argue you never could tell. If the circuit was flat in 1D, you could almost never tell. 2D, it depends on maybe exactly what circuit you put in. But there are some circuits where you still wouldn't be able to tell a laptop from a quantum computer. But this year, that claim was really definitively overturned, Google's claim, by a tensor network method running in kind of an exact mode with some very surgical errors sort of put in by hand. So this is a big, kind of seminal powerhouse work by Pen Zhang and his collaborators in Beijing, again, using tensor networks. We had a kind of a parallel work where we were trying to do the same thing, but still just using MPS level technology, just sort of beefed up a bit with some extra algorithm ideas. And I would say we like tied Google's result or got awfully close to tying it now, using these more pedestrian kind of out of the box kind of tools. So this is just showing our fidelity in this one mode getting really close. And then in the best mode, I'll show you in a second, kind of plunging into the region that matches Google's. The main trick there is this idea called closed simulation, where open means you actually have the whole state afterwards. That's that TEBD idea. Weak means you just generate bit strings, but you have no idea about the amplitude. Closed is in between. It's saying you go for a certain bit string. So you say, I want to simulate this bit string at the end, but also tell me the amplitude. So I get to find out if it was negative, positive, what size. So this is easier to do. One way to see that is it's two open simulations back to back. Like you start from the left and start from the right and you simulate to the middle. So you at least save a factor of 2 on the depth. You just do 2 times calculations that might be a lot easier. So there's all these tricks we can do where we're sort of going forward and backwards in time on a classical computer, and that can save us a lot. Right, that's like a square root speed up basically of an exponential. So there's all kinds of tricks still happening in this game. So kind of maybe last few slides to wrap this up. Basically, what are some takeaways right now? And I'd say there's still a lot happening in this topic. This is like an evolving topic. Entanglement has to be part of what makes quantum algorithms powerful. It has to be, because if it's not, we can simulate it. So there has to be some amount of entanglement going on. But I would say that up until now, there hasn't been a lot of precision in talking about how much. It's just been saying, this algorithm generates entanglement, maybe a lot. This one generates some, but it's important to understand how much in a very precise sense of like, okay, there's this much entanglement in this geometry, meaning it's kind of, PEP simulable, but not MPS simulable. These much more precise statements, I think, have to start being made in order to understand where's the really hard stuff. So is the entanglement really high in the most popular algorithms, Shor's, Grover's, in what instances, or is it only moderate, and can we simulate it? I would say this is not fully understood yet in all these cases, but it's starting to be. So there's a really great paper from this summer on the archive where some people figured out sometimes you can do shortcuts in QAOA. Not all of you know QAOA, but it's basically a way to solve certain graph theory problems using variational quantum algorithms. And it's found at the same time too, one group found there is an exponentially high entanglement barrier, but another group found that you can just tunnel through that barrier. So you just cap the chi off at like 20 or something, and then you can just like cut through the entanglement barrier and you kind of dodge around it, and you still get a very good answer. So there's all kinds of interesting back and forth happening. The entanglement in Grover's algorithm is also, I think, kind of still something that needs to be investigated more closely, I would argue, and it might be more application specific than people thought. So for that, see Linjan's talk on Friday for Grover, so just mentioning that, and other algorithms too. So he has a talk about simulating, and he also has a talk about some of these tensor network power tools. I didn't put it on here, but machine learning is another one where we need to know what's the role of entanglement. So see Ian's talk about that. And then lastly, I'd say a really, really promising direction, I think, still for quantum computing is simulation. So the idea of saying, let's make our quantum computer mimic some quantum system, and then let's use it to simulate it in a very it's like a clean experiment, without all the grit and noise of real materials. So there'll be two really nice talks about this on Friday. So one is Michael Fossfeig, and he'll be showing ways that combine matrix product state ideas to use qubits more efficiently to simulate time evolution of quantum systems. So sort of threading all these ideas together. It's actually using tensor networks back for the quantum computer. So it's almost like tensor networks become a smart way to program and use quantum computers. So there's this real back and forth interplay where one technology is against the other one, but then sometimes it's in support of the other one. And so I think he'll make that clear on Friday. And also Tim Shea on Friday will talk about another interesting way of doing quantum simulation, where if you mix in measurements, you can actually use measurements to prepare very interesting states of matter, these topologically ordered SPT, topologically ordered states of matter in shallow circuits, but you have to put in measurements as well. So these, I think, are very promising directions. And they're less so much in the mode of, can we just use a quantum computer as a hammer on a big hard problem, but more as like a surgical scalpel to kind of prepare beautiful states of matter and this kind of thing. So I think that's a great direction. So I'll just wrap up by saying tensor networks are this very efficient tool to work in high dimensional spaces. It's really like kind of in linear algebra in exponentially high dimensional spaces is one way to view it. It's really kind of perfectly made for simulating quantum algorithms, because quantum circuits are tensor networks. So they're really kind of hand in glove. In fact, something I didn't have time to explain is that actually the reverse is often true too. So all MPS are quantum circuits also, and so are all trees. And so there's like this kind of interesting back and forth dictionary where an MPS is a quantum circuit. So you can actually run an MPS on a quantum computer as well. And then lastly, another thing I wish I'd had more time to unpack, but maybe that part about the QFT was a little bit of it, where there's this kind of amazing boundary, I think, starting to be defined, where some quantum algorithms are being brought back from the quantum world back into the classical world as quantum-inspired algorithms. So it might be that some of the great insights of quantum computing, like the QFT, which I think really was like a great insight, actually are something we could be using now, like today, and it might be a smart way to program a regular computer too. So I think that's another direction. So thanks for your questions and attention, and I'll take any more questions you might have. Thanks.
So
Mhm.
at least I'm very lost because I'm not very into the literature. But is the idea for like in the quantum computing case, when you do MPS on this two qubits, it's basically you're kind of projecting an entangled state into tensor states
Mhm.
by higher dimensions. Is that kind of what's going on there?
Yeah, like you mean when you put a 2-qubit gate onto
Yeah.
two of them, and
Yeah.
Mhm. That's right. I mean, you could think of it as you're taking the whole Hilbert space and you're organizing it into these like shells,
Mhm.
and then the product state of all zeros is like this smallest shell at the bottom,
Right.
and it's really easy. We can write it down by hand as I showed. Then you bring this gate, and it sort of pushes you up, whether you want to or not, up into like a higher shell, and then you can. That's when you can make these moves about. If I want accuracy, I just have to live with that. I just have to move through these shells. And that's kind of some of the original notion. If you go back to the 90s and they'd say, why is this hard? They knew that you'd be rapidly moving through these shells off into something very big and exponential. But at the time, ideas about entanglement weren't as refined. And like a lot of that happened in the early 2000s. And they didn't always see that there were, you might think you're off in that exponential space, but you're actually moving along some kind of almost like a tangent vector. And you're really staying closer to these lower shells. And you can project back down onto them. So it's like you apply a projection operator, yeah, back into these lower manifolds.
Product states that still well represents the
Mhm. Yeah, exactly. And you can think of these tensor product states as being the coarsest view of them would be it's a sum of product states. So you're just saying now instead of one product state, I'm in a sum of many product states. But the extra twist is that like literal twist is that you don't make that sum in the original basis. If you could, it's just that would immediately bring an exponential in very fast. Like that Hadamard state would actually be a sum of exponentially many states right away. So what you do is you also rotate your basis. And when you do that, you can uncover the low rank structure. So it's like sums of product states in these kind of rotating bases. They rotate as you go through the MPS left to right. And that's when you bring all that together, that's the whole story for these. Yeah. Mm-hmm. Yeah.
You mentioned at one point that the bond dimension in the worst case doubles when
Mhm.
you apply a local unitary. Sorry, a 2-qubit.
Yeah, 2-qubit.
I didn't quite catch the explanation. I think I
Mhm.
didn't quite understand it. Would you be able to
Sure.
explain that?
No problem. Yeah, it's not obvious at all. It's a theorem from the SVD. So if you have, it's not something that you can just see right away. You have to kind of go back through the theorems of SVD. So if you and someone tell me if I got this wrong, but I'm pretty sure I made the slide pretty late last night. But you apply this gate, and now you just can think of this as being a rather arbitrary tensor with these 4 indices. But then if you remember that the sizes here are chi to chi, and we're splitting them that way, then it's just a counting thing of if when you kind of go back through the SVD, well, actually, that's really just it in this case. It's actually, in the simplest case, it's just square, and it's a 2 chi by 2 chi. That's really it. In the more general case, the chi's might be different on the different sides. So there might be like a chi 1 and a chi 2, and then it becomes a min. It's like min over 2 chi 1 or 2 chi 2. And that just comes from how the SVD works. You square the matrix both ways. And then you look at like what's the size of the kernel or null space on the two sides. So there's just like a linear algebra understanding.
So you're the thing on the top right,
Mhm.
sort of 2 things here and 2 things here, and both of those have 2 chi's.
Mhm.
The 2 of the chi 5.
Yeah, exactly.
Just a small related question.
Mhm.
Is it true that if you sort of pick a random sort of generic unitary, you start hitting your initial state with unitaries? I suppose your initial state is completely separable, and you start hitting it with unitaries, you generally going to expect to sort of saturate, come close to saturating that.
Mhm. Like you mean if you just put sort of random unitaries down onto your initial state? Random 2-qubit. That's right. And so that's what Google was really basing their whole claim on, was saying, we know for sure that will take you somewhere hard, that it'll take you to some totally perfectly well-defined state, but which is hard for any computer to really store the whole thing or sort of efficiently query that state or do really anything with it. So you're totally right.
The one dimension, so the thing does double, like in almost all cases, that you start randomly applying.
That's right. Yeah, it'll just take off to the moon. And so the only thing that was a bit off about what Google said was this may be more editorializing, but they talked a little bit about out both sides of the mouth. They said, we did this thing that's hard, But then they said, but we only did it approximately. So that was a little bit of a game because they were saying we did something, you know, it's like I made $1 million, but only really one of those $1 million. It's like, well, that's not that hard. I mean, you know, okay, you know, so they defined a very hard problem, but then you actually have to do the problem in order to say you did something hard. And they only did, you know, 0.2% of the hard thing, which is still really hard, but it's not as hard as doing 100% of the hard thing. So that was just me making a side comment about that. But the truth is what you said, is that the circuit always defines a very hard problem in general that is indeed really hard for everybody and pretty hard even for a quantum computer without error correction. Yeah. Mm-hmm.
I was
Mm-hmm.
just wondering, like, in a quantum computer, obviously, like you said, the desire then would be to try and implement some sort of circuit on lots of qubits that was very entangling.
Mm-hmm.
But is there maybe something physical that actually on a quantum computer it's hard, like the more entanglement you generate, I don't know, the less coherence time you have amongst your qubits or something like that is also a bottleneck even in a quantum computer.
That's a really good question, I think. So
just repeat it for everyone.
like if I got your question, I think it's like you're saying maybe not only is it hard to generate a highly entangled state, just in the sense you have to apply more gates, you know, and maybe, you know, if you make a mistake earlier, you might be already, you know, kind of hosed or something, and now you're already making errors. But it might even be worse than that. You're saying like maybe if it's highly entangled, that there's sort of more avenues for errors to come in. I don't think I can say anything too smart on the record about that, but I do kind of feel like I've been talking to some friends about that kind of thing, and I do have some sense that there might be more, like more work needed there to exactly quantify that kind of thing. I mean, it might have to be sort of defined a little more in the sense of saying that that state has some kind of property that I consider as some kind of resource. Like an example would be in Grover's algorithm, you make a sort of initial superposition of everything, so exponentially many things, which is just that simple Hadamard state. But what you do is you call an oracle that goes in and tags, like say one of the states for you to be -1, but it's not -1, it's -1 over square root of 2 to the n. So it's this little wisp of the thing that is all your problem is in that. So, you know, then if someone comes along and like bumps the table that the quantum computer is on, you know, what if that one amplitude goes away? Your whole answer is gone, you know. So it's just to say that in some of these cases, these states might be really, really delicate in ways that could be quantified better. So I think it's an urgent problem that needs to probably be more like brought to light. I have heard about some work that quantifies this in the sense it says that random states in the Hilbert space, which are the most entangled, among the most entangled, can be like argued not to be useful for practical things. So there is some work quantifying that, but I don't know how far that work goes right now in terms of really being precise to sort of this algorithm at this depth of circuit. I think it's probably a bit of an open area. Mm-hmm. Yeah, Ian.
Well, all you're based on the idea of trunking the lower similar values.
Mm-hmm.
Is there any danger in that? You require those, therefore in the algorithm you lost them and you can't get them back.
Mm-hmm. Yeah, I like that question. Yeah, that can be the case. Yes, so there can be cases where you have to like kind of condition your problem when you do the truncations, if that's the right word, toward the goal you have for it. I mean, so actually, Grover's algorithm is kind of like that, actually, where you might say, we can throw this away. It's only 1 over square root of 2 to the n in size, but it's actually -1 is square root of 2. So that's the whole answer to the problem is that one thing. That's kind of an example where there can be this very delicate filament of entanglement, and then really that's the whole problem. But a more concrete example is there's a work by some of my colleagues at Flatiron recently where they were using MPS to do high dimensional integration. So they were saying we can kind of machine learn functions into MPS. Is really neat technology. There's this whole thread of like Russian mathematics coming into tensor networks that's really kind of amazing, and it's called like quantized tensor train, and it's this idea of putting functions into matrix product states. And so when you do that, there's fast algorithms to compute the integral, and the thing they were doing, they realized is that they were doing truncations, but then or doing kind of truncations and or trying to optimize the next step of the machine learning process to like which data point should we go after next. And they realized that their initial thing worked, but could be better. And what they did is they would like pre-weight parts of their algorithm by the integral operator. So you would bring the integral operator on and say, given what we have now, telling our algorithm it's going to be doing the integral, can we truncate better or seek better what they call pivots for doing the integral? So there may be a lot of things like that. So actually in machine learning with tensor networks, I think this is needed. So this original idea of using DMRG there somewhat was only like a moderate success. It had some issues. And it could be that there needs to be like a reweighted SVD that's weighted through the labels of supervised learning. And that probably needs to be figured out, actually. So hopefully that answers, yeah. John.
Miles, there's a question in the chat. Thanks for the great talk. I think SVD can partially do noise filtering to some degree, throwing away the small singular value. Will this do anything like noise filtering for quantum circuits using a tensor network simulator?
Oh, that's a great idea. I mean, I think possibly, yes, I don't, yeah, it'd probably have to be, tried a bit to see in what mode that would be useful. In the classical simulations as they are, we wouldn't have a need of that in the sense of we can control the gates we apply perfectly. But I mean, if we applied somehow, like one way that might be interesting is if we mimic the same noise that's in the experiment. So what if we mimic calibration errors in the simulations? Can we then use the simulations to denoise something about the state afterward? How you could make that into like an honest thing, I don't know, because you'd have to somehow know the calibration errors you made in the experiment to put into the simulation, and then maybe you just fix them right away if you knew them anyway. So I don't quite know how to close that loop, but I think I think there's an interesting direction there, and that is a whole other mode of using tensor networks that I think is underappreciated by the physics community right now, which is that we often think of the truncations as being that we're shaving away stuff that we want. But you also can think of it as shaving away noise that you don't want. And then it actually can like learn the remaining elements better, and so there's a sense in which the SVD is doing learning too, quite literally. So. Yeah, okay.
Let's thank Miles again.
Thanks, everybody.